So for number 2, we need to use the washer method to figure out a volume enclosed by revolving a region. So we have a few bounds. We have the function y equals 1 over x as one of our bounds. We have y equals 0, and we have x equals 1 and x equals 3. So it's usually in your best interest for this type of problem to graph this first. And we're rotating about the line y equals -1. So I'll put, this is the line that we're rotating about. So if we were to graph this, we have, let's put all the straight lines in first. So we have y equals 0, in other words, the x-axis. We have x equals 1. And we have x equals 3. And we have the graph y equals 1 over x. So y equals 1 over x is going to start here and go down. Keep in mind, I'm only graphing the part that we're interested in between x equals 1 and 3. So this section of graph that I'm shading here is our enclosed area, and we're rotating about this dotted line, y equals -1. So if we're going to use the standard washer method, you can see that in every sliver that we cut of this area, our final result is going to look like a washer, because we're going to have two rings, and we're only interested in the area of the outer section, not the intersection. So what we need to figure out is how do we represent that as an integral. So the area of a ring section like that is the radius, pi times the radius squared of the outer minus pi times the radius squared of the inner. So we have pi r1 squared minus pi r2 squared. And the washer method says that if you integrate that area over your range of x values, then you'll get the volume of the resulting shape. So if we integrate this, we're going to have dx. That will be our volume. So of course we can pull a pi outside of that. So now we need to figure out what are our outer and inner radii. So our outer radius are, if you think about this here, since we're rotating about this line, the outer radius is going to be determined by y equals 1 over x. This line here, because that's going to be the higher one. So when we rotate it around, it's going to be the outer radius of each ring. So what you need to do, though, is the radius is the distance from the center to the edge. So our center is y equals -1. So what we need is an expression for how far is it from y equals -1 to this line. Well, it's this y distance, 1 over x, plus 1, because 1 over x only gives you the y value to the x-axis, this distance, at each x. But we want to go all the way down to y equals -1, so that we have to add an additional 1. So our radius here is 1 plus 1 over x, and we have to square it. So what's our inner radius? Well, our inner radius is just y equals 0 the whole time, because that's going to be the inner, and the outer is changing along 1 over x. So our inner radius is just 1 at all times. And 1, we don't even have to square that, because we know that it's just going to be 1. And what are we integrating from? We're integrating from x equals 1 to 3. So this right here is our integral, and we just need to write this in a simpler fashion. So what do we have here? For the next step, we have pi still on the outside, integrating from 1 to 3. If we FOILed this out, 1 plus 1 over x quantity squared, we would get 1 plus 2 over x plus 1 over x squared. And we're subtracting 1 dx. You can see here that this 1 and this -1 would cancel out. And we can write this with a common denominator because we have x and x squared. That's pretty simple to do. And I think the final form has the pi on the inside, so I'm going to write it like that instead. So what would our numerator be if we were to add these two terms together with a common denominator? Well, our common denominator would be x squared, and this would just be 2x plus 1 over x squared. So we have pi times 2x plus 1 over x squared dx. And again, if you were to evaluate that integral, that would give you the volume of this particular rotation using the washer method.